Section 3. A note on impedance. Once converted into voltage by the microphone capsule, our sound enters the electrical realm. We have talked about voltages so far because that is what is physically changed in the processes we described. However, when those voltages are transmitted along conductors like cables, it is more convenient to discuss about currents. Both are linked by resistance or impedance. What is impedance? There, components transmitting the current, like cables, can alter it. They have electrical characteristics like resistance, which has some resemblance to friction in the mechanical world. Because currents transmitted by audio equipment vary with time, alternating currents are either generated or modulated by transducers, the correct concept to use is impedance instead of resistance. Why? According to the laws of physics, two phenomena appear when tensions or currents change with time. A magnetic field appears, induction effect, and electrical charge is stored in the conductor, capacitance effect, both increasing the factors impeding, hence the terms impedance, the current from flowing to its destination. Inductive reactance XL, from the induction effect, and capacitive reactance XC, from the capacitance effect, form the reactance X. X is XL plus XC, where XL is 2 times pi times nu times L, and XC is 1 over, open parentheses, 2 times pi times nu times C, close parentheses. L is the inductance, measured in henries, of the material used, and C is its capacitance, measured in farads. Note that inductive reactance is proportional to the audio frequency nu, while capacitive reactance is inversely proportional to it. This means that at low frequencies, inductive reactance is small, but capacitive reactance is large, the opposite being true at high frequencies. Impedance is simply the sum of those two effects, resistance and reactance. The symbol for impedance is Z, and it is measured in ohms, like resistance. Z is the square root of R squared plus X squared, where R is the resistance and X the reactance. That is where the Z on your audio interface comes from. High Z, low Z, what is that about? Because different devices translate pressure into electricity, like microphones, or transport electricity, like cables, in different ways by design, they have different impedances and thus transport current with varying friction. There generally are two types of impedances related to audio equipment: high impedance, usually labeled high Z, and low impedance, usually labeled low Z. Low impedance devices, from 0 to 10 kilo ohms, where 1 kilo ohm is 1000 ohm, include most microphones, interface inputs for microphones, and most interface outputs. For example, my interface has 3 types of input impedances: microphone at 2400 ohms, a mic or line input at 10 kilo ohm, and a guitar input at 1 mega ohm. The output is at 100 ohm. High impedance devices greater than 10 kilo ohms include instruments outputs generally between 7 and 20 kilo ohms and interface instrument inputs in the 1 mega ohm range. Why is impedance important? Because in some situations, knowing the source and destination device impedances, destination impedance can also be called the load, can help resolve audio issues like loss of sound quality. Most of the time, impedance issues are transparent because of the way audio equipment is built. To ensure a problemless signal transmission, the target impedance is at least 10 times that of the source. This ensures that voltages are properly transferred across multiple devices so that the signal quality is preserved. Section 4. Cables. Why do I care about cables? Connecting the microphone to whatever comes next in the signal chain is an audio cable. An audio cable is made of conducting material surrounded by shielding material. Its role at this stage is to carry the electrical current generated by the microphone to the preamp. Because electrical current is subject to interferences by other electrical devices or magnetic devices, and because one can generate the other, shielding is needed so that the electrical current carrying all the information of the recorded sound can arrive at its destination safe and sound. Cable impedance effects are generally negligible because they come into effect only when the highest frequency present in the signal corresponds to about 10 times the cable length. For example, a 20 kHz frequency is equivalent to a wavelength of about 10 kilometers. Equation 2 applies, but here speed is the speed of light, that is, the speed at which electromagnetic waves travel through the medium. Because there is a resistance, impedance to the progression of those waves in the cable, the waves do not travel at the full speed of light at around 300,000 meters per second, but at a fraction of that speed. The fraction is called the velocity factor Vf, and it depends, without any surprise, on the capacitance C and the inductance L of the material used for the cable. Balanced and unbalanced cables. What are they? There are two types of cables, unbalanced and balanced. Unbalanced cables use only two conductors, a central conductor carrying the changing current and a shield connected to the ground. Examples of unbalanced cables are quarter-inch guitar cables or older RCA connectors. Balanced cables use three conductors, two in the middle to carrying the changing current, and the last one for shielding purposes. The advantage of balanced cables is that because there are two conductors, they can be designed so that interferences cancel out. Examples of balanced cables are XLR connectors and TRS connectors. While TRS does stand for tip ring sleeve, XLR does not stand for ground, X, L left right, as many people think it does. The truth is related to how cables were once built. Most images found on the web, being legally protected against copying, simply type balanced, unbalanced connectors into any search engine, select images, et voila. All sorts of nicely drawn connectors, from RCA to TS to TRS to XLR. It is important to know the difference, because unbalanced cables should only be connected to other unbalanced cables to avoid ground loop issues. Cables can be recognized by their type to be balanced or unbalanced, see above. In case of doubt, device manufacturers usually indicate which type of connector you are dealing with. Section 5. Microphone preamplifiers. What is a microphone preamplifier? When the sound has been captured by the microphone, we should say read by the microphone, it comes out in the form of electrical current tension values. Those values are usually very small since the air pressure moving the membrane is not very strong. On average, 0.1 millivolt for a ribbon microphone and 10 millivolt for a dynamic microphone. Guitar pickup levels are higher at 150 to 200 millivolts. Audio equipment is designed to work with much higher voltages, around 1 volt, the line level we previously defined, so this electrical current must be amplified. That is the role of preamplifiers or preamps or pre's. Help the signal gain power. How these devices amplify the signal is important, since we know that any electronic component put in the electrical flow will alter the original signal. How does a preamp work? A preamp consists in a chain of electronic components. First, the input, usually a balanced male XLR input, since that is what microphones usually use as output. The next set of components can be put under the banner of the input section and is optional, depending on the preamp model. Some have these components and more, some have none. The first component in the input is usually a phantom power source for condenser microphones. The next component might be a polarity switch, which will allow you to flip the polarity of the incoming signal. Then a pad switch might allow you to make the sound quieter if it is too loud by inserting a set of coupled resistances in series in the circuit. Finally, a resistance inserted in parallel with the circuit might be available to change the impedance of the circuit. The switch itself might be labeled low Z, for example. Once these formalities have been executed, the real deal starts with the main gain stage and the actual increase in tension for which the preamp is built. This increase is achieved by inserting in the circuit a series of electronic components such as transistors, vacuum tubes, operational amplifiers, op-amps, and/or a combination of all the above, each raising the gain by some fixed amount called gain stage. These components can change the way the signal is shaped and add frequencies that the original signal did not have. That is where the secret sauce of mic pre's is made and a jealously kept secret. If those effects are not desired, a so-called clean signal is preferred. A copy of the original signal is inserted after the gain stage and mixed with the processed signal to try and get rid of the unwanted effects. This works because the gain stage flips the polarity of the signal. That is how transistors work. Finally, the output buffer takes the amplified signal and feeds it to the next device in the signal chain. Other components, such as a trim switch, might help you adapt the pre's output to the next device input sensitivity. One such line of components, built to amplify an analog signal, is called a channel. You will hear engineers talk about 4 channels of input. This means that they can record 4 analog sources and amplify those signals simultaneously. How do we categorize preamps? Preamps can be classified in multiple fashions, but the most useful one is the one which categorizes them by what type of amplifier are used for the main gain stage: solid state or tube. Solid state devices are devices which have current flow only through solid matter, by opposition to tube devices which have current go through vacuum tubes. Solid-state amplifiers include all types of transistors, bipolar junction transistors, field effect transistors, and op-amps. These transistors can be put on integrated circuits, IC, or separately integrated in the signal flow, the famous discrete design, which minimizes interferences between signals in the device itself. There are preamps which gain stage the signal through a solid-state amplifier before sending it through a tube. Technically speaking, they're still a solid-state preamp. On the topic of tube versus solid-state amplifier and which ones sound the best, we are touching upon religion, much like in the analog versus digital debate. Only sensible thing which can be said is that people favor the tube or analog sound because those designs produce mostly even harmonics, which are musical to our ears, the famous warmth that people talk about. Tube amps are usually both noisier and less accurate than solid-state amps, but we have learned to like the old sound better, and that is what we now expect. I strongly believe that if we were to present both amplified sounds to a Martian audiophile, our Martian friend would prefer the solid-state digital sound for its better accuracy. I want to buy a preamp, help me! In Table 5, classic preamps are listed. They are chosen because they were made from respected and well-known manufacturers. The features column contains the number of channels, the type of electronics inside, and the design. The last column gives an indication on how most people perceive the sound coming out of the preamp. Do not quote me on that. Table 5 has 6 columns: manufacturer, model, features, price, price per channel, and sound. Manufacturers represented are A-Designs, API, Avalon, BAE Audio, FMR Audio, Focusrite, George Massenburg Labs, Golden Age, Res Design, Great River, Neve, Telefunken, True Systems, and Universal Audio. Prices range from $350 to $3,600. Another classification considers the design of the internals of the preamp. There are 3 main designs: Class A, Class B, and Class AB. Class A designs signal the fact that both the positive and negative voltages are simultaneously amplified. This means that the output signal's shape is very close to the original, no distortion. But it also means that the device will run very hot since it is functioning all the time. This means more risk of failure. Class B solves the problem by having 2 distinct amplifiers, one to amplify the positive and one the negative voltages. The disadvantage is that at the crossover between both sides, the signal may be distorted because the amplifying devices take some small time to start working. As a result, they are perceived to be less accurate than their Class A counterparts. Their third type, Class AB, tries to take the best of both worlds by having the following amplifier starting up before the crossover is reached, so that when it does, the distortion is minimized. As you can see, Class A does not mean that it is the best class, only that it is one design amongst others. Manufacturers have been very creative in bundling different devices together in a single case product, appearing as a single device to the unsuspecting consumer. Such bundles include the audio interface, which consists in one or more mic preamps, along with AD and DA converters. Another bundle is the channel strip, putting together mic preamps and outboard gear, see Chapter 2, Section 7, such as EQ, EQ stands for equalizer, and compressors. To close this short summary of how preamps work, I have always wondered what the difference was between, on one hand, turning the knob on the preamp clockwise, and on the other, turning the knob on my speakers clockwise. To me, both knob turning exercises achieve the same thing, making the music louder. As it turns out, the difference is significant. The knob on the preamp amplifies the signal before processing. It gives the processors